Now, in this situation where we have non-concurrent or parallel planar forces, we actually have to consider the generation of moments of force about a point. That is, these forces are no longer concurrent or collinear. That is, there will be multiple moment arms these forces will be acting on that is going to create a tendency for rotation. Thus, for us to have static equilibrium, we must satisfy the following equations. We have to ensure the summation of forces with the x direction is equal to 0. We have to ensure that the summation of forces within the y direction is equal to 0. And we also have to ensure the summation of moments existing in the z direction are equal to 0. To see this in action, let's consider a crane that has a mass of 1,000 kilograms, and this crane is used to lift a 2,400 kilogram crate. Now the mass of the crane is placed at G, the center of gravity, and our crane is supported by a pin at A and a rocker at B. The distance between our pin and rocker is 1.50 meters. And the horizontal distance between our pin and rocker and our center of gravity is 2.00 meters. And the horizontal distance between our center of gravity and the weight of the crate is 4.00 meters. We want to determine the components of the reactionary forces at A and B. For us to begin, we are going to draw a free body diagram. Our pin provides reactionary force in the x and y direction, i.e. RAX and RAY. Our roller or rocker provides reactionary force in the x direction, i.e. RBX. The weight of the crane is 9,810 newtons, and this is applied at point G. And the weight of the crate is 23,500 newtons, and this is applied at the end. Now we will start by applying the summation of forces in the y direction. That is, we can say the sum of the forces in the y direction is equal to 0. And we see RAY minus the weight of the crane minus the weight of the crate, which sums to 33,300 newtons, is equal to 0. Thus, we can say the reactionary force at A in the y direction is 33.3 kilonewtons. Next, we'll apply the summation of forces in the x direction. We'd have RAX plus RBX is equal to 0. Currently, we have one equation and two unknowns. Thus, we can apply the summation of moments about a point. In this situation, we're going to pick point A because we have two forces acting on point A. And thus, we'll have the fewest number of moment arms to consider. Now, recalling counterclockwise is positive and clockwise is negative, when we take the summation of moments about point A and set it equal to 0, we'd have RBX times 1.50 meters minus 9,810 newtons times 2.00 meters minus 23,500 newtons times 6.00 meters. And these are equal to 0. Thus, we can say RBX is equal to 19,600 plus 141,000 newton meters per 1.50 meters, or RBX is equal to 107 kilonewtons. Now with RBX known, we can go back to the summation of forces within the x direction, where we had RAX plus RBX was equal to 0. Or RAX is equal to minus RBX, which is equal to minus 107 kilonewtons.